Hey guys, today we're going to look at how to analyze graphs and examine their properties. So for the next few graphs, what we're going to have a look at is the domain, the range, the intercepts, the increasing and decreasing behavior, extrema, whether it's relative, absolute, and their end behavior using the graph alone. So first, remember that for all of these intervals, we're only going to use interval notation. And then for everything else that are coordinates, obviously you have to write it as coordinates. So first of all, let's start with domain. Remember that the domain represents all of the x values that are defined for your function. So for each one, you're looking at how far to the left does it go, how far to the right does it go, and if we have to stop somewhere in the middle in terms of your x values. So if we look at this particular graph, we see that it does open to the left forever, which is to indicate that it would start at negative infinity. And then if I continue reading the graph from left to right, there are no breaks in between, and it opens to the right forever, which is positive infinity. So the domain of this particular graph would be from negative infinity to positive infinity. Now, when you're looking at the range represents all of the y values that are defined in your function. So you got to look at how low does it go to how high does it go, and if we have to stop somewhere in between because there is some kind of vertical break. In this particular graph, we see that it does go down forever, so it will start at negative infinity. Then as I read my graph continuing going upwards, all of these y values are included, and it does continue to go up forever to positive infinity. Now your x-intercepts are when your graph touches your x-axis, and we can see that we have two x-intercepts here. And we have to write this as coordinates. So our first x-intercept is negative 3, 0, and 0, 0. Then for a y-intercept, that's when your graph touches your y-axis, which occurs at 0, 0. Now 0, 0, which is the point of origin, would be considered both an x and a y-intercept if your graph goes through it, because that's where your x-axis and your y-axis meet. Now for increasing and decreasing behavior. I'm a visual learner, so I like to draw on my graphs. So whenever we're trying to determine increasing and decreasing behavior, we have to read the graph from left to right. And you're going to write these intervals in terms of x only, meaning that we're only writing down the x values. So for example, when we're writing increasing behavior, you would tell me from what x does it start increasing to what x does it stop increasing. So when I'm looking at my graph, I see that at first my graph is going up, and then at the points where it stops increasing, I like to write down that x value, and this is x is negative 2. Now I do this as a visual reminder that when I'm writing my intervals, we're only writing the x's. So now I continue and my graph is decreasing until x is equal to 0, and then it starts increasing again to infinity. So additionally, I like to keep the negative infinity and the positive infinity on the left and the right side of my graphs. So when I'm writing these intervals, I know that if I'm starting on the very, very left side, it does start at negative infinity. And if your interval ends at the very right of the graph, it'll end at positive infinity. When you have your arrows drawn in, you can see that the graph is increasing twice on this graph. So we have two intervals that would describe that the graph is increasing. Now, on the left side, we see that it starts increasing at negative infinity, and then it stops increasing at negative 2. Now this is important. We only use parentheses for all of these intervals because we are never going to include these values. And that is because at x is equal to negative 2, that's where it's shifting directions. It went from positive, or rather it went from increasing and then to decreasing. So at x is equal to negative 2, it is neither increasing nor decreasing because it is changing directions. So we never include those values. Now moving on, we do have this second interval where it is increasing. So it starts increasing at 0, and then it increases the rest of my graph so towards infinity. For decreasing, we only have one decreasing interval. That's this one arrow that's going down. It starts decreasing at x is equal to -2, and it stops decreasing at 0. Now your extrema. We have two types of extrema. We have relative and absolute. Relative is like your second place, whereas absolute is the absolute minimum or maximum. Extrema is the word that we use to describe minimums and maximums, so it just encompasses both. So when you're looking for maximums, you're looking for those hills on your graph. So for example, right here at x is equal to -2 and 4, the y value 4, the coordinate, this is a maximum because it is a hill. But we can see that there's more going on above that point, so it can't be an absolute. An absolute maximum would mean that there is nothing above that point. So this would be considered a relative maximum. Versus this point right here, this is the one that I would consider a little dip. This is a minimum. Now again, we have to check, is there anything below this point? And I see that we have graph behavior below 0, 0, meaning that is not the absolute minimum. If it was the absolute minimum, there would be absolutely nothing below it. So this would be considered a relative minimum. When we're writing our extrema, it's important to make sure that we write down the coordinates. So for the relative maximum, we have a relative maximum at -2, 4. And we have a relative minimum at 0, 0. Now for absolute, absolute would mean that there's nothing above it, but we can see that this graph goes down forever and it goes up forever. Therefore, there is no absolute extrema. Now, again, important to note, infinity and negative infinity are never considered points of extrema. Your extrema are coordinates. You have to be able to put a dot on it. They must represent real numbers. And since infinity is not technically a real number, we cannot state that it is an extrema. Now finally, our end behavior. All end behavior statements look the same, and this is their basic format. It'll read as x is approaching blank, f of x is approaching blank. Now I left these blank because this is the part that you would fill in. The first part of each end behavior statement is letting you know whether we're looking at the left or the right side of the graph. Now it does not matter which one you choose to write first because all graphs have two ends, the left and the right, which we can see here as I indicated in purple. Those are considered the ends of your graph. So if I'm looking at the left side, if you're going to the left, your x values are negative and they would continue the negative. So the first part of your end behavior statement would read as x is approaching negative infinity. This means I'm looking at the left side of my graph. I'm going to check out what the y values, which is f of x, are doing on the left side of the graph. As I look on the left side, I see that my graph is going down. And since it's going down, that means f of x, your y values, are going towards negative infinity. Now for the right side, as you go to the right side of the graph, your numbers are all positive, and if you continue going to the right forever, that means that x is approaching positive infinity. And now when I look at the right side of my graph, I see that the y values are going up forever, so f of x is approaching positive infinity. Let's have a look at another graph. Now, when we're writing out our domain, I'm checking out how far to the left does it go and how far to the right does it go. And it goes forever to the left and to the right, as you can see that the graph is opening up and outwards. So we would say that the domain is negative infinity to infinity. Now the range. The range, I'm going to look at the smallest y value to the largest y value. And I can see here that the smallest y value is 0. Now I am including the 0 because your function does touch the point where y is equal to 0. And since it touches, it is included. So this would be from 0, and then it opens up forever, so to infinity. My x-intercepts are right here where it touches your x-axis, and these are -1, 0, and 1, 0. Now again, your function can have many x-intercepts. It could have only one x-intercept. It could have no x-intercept. It doesn't matter. But every function will have exactly one y-intercept. And in this case, that one y-intercept is at the point 0, 1. Now the reason for this is that all y-intercepts have an x value of 0. So if you have multiple y-intercepts, that means that x is equal to 0 would repeat on the function. And functions have no x values that would repeat. So if that were to happen, that means that what the graph you're looking at is not considered a function. Okay, so now I'm going to determine increasing and decreasing behavior. So as always, I'm going to label my graph here. The left side is infinity, the right side is, the left side is negative infinity, the right side is positive infinity. Remember, I write these because we're writing these intervals in terms of x. So we don't want to get confused and say positive infinity because it's up here, but more negative infinity because it's on the left. Now, when we're going from left to right, we see that the graph is starting to go down until this point, which is where x is equal to -1. Then it increases until x is equal to 0. Then it decreases again until x is equal to 1. And finally, it is increasing the rest of the time until x approaches infinity. So for increasing behavior, we do have two parts of the graph that are increasing. So we're going to have these two intervals, one being it starts increasing from -1 to 0, and then it continues increasing again from 1 to infinity. Now for decreasing, it starts decreasing from the very left of the graph, so from -infinity until -1. And then it decreases again from 0 to 1. Now for our extrema. Before I go ahead and start writing out my relative and absolute, I like to just go ahead and look at my graph and look for those hills and dips, and then go ahead and label what they are so I know what to fill in. As you can see, these are two minimums. And because there is nothing below it, you see how the graph doesn't come back down. We have no more behavior below those points. Both of them are absolute minimums. And this right here, this is a little hill. So this would be a maximum. But we do see that we have more values above that maximum. So this would be considered a relative maximum. And this would be all of the extrema that we have on this graph. In terms of your graphs, you can have as many relative and absolute extrema as the graph wants to have, I guess. It could have only relative extrema, it could have only absolute extrema, it could have no extrema at all. So it all just depends on the graph's behavior. Your extrema only occur when your graph changes behavior. So that means if it's changing from decreasing to increasing, as we see here, this is a minimum. If it's changing from increasing to decreasing, that would be considered a maximum. So that's another way of checking whether you have extrema at those points, is making sure that those are those values where it changes behavior. So for this graph, we have only a relative max, and it occurs at 0, 1. Then for our absolute extrema, we only have two absolute minimums. And you always make sure to give me the coordinates. So the first coordinate for the absolute minimums would be -1, 0, and then the other is at 1, 0. Now let's have a look at our end behavior. If I want to write the end behavior statement for the left, I would start off as x is approaching -infinity. Now I'm going to have a look at what my y values are doing, so I know what f of x is approaching. On the left side of my graph, that's over here, we can see that the graph is going up forever. So f of x would be approaching positive infinity. On the right side of the graph, we would write as x is approaching positive infinity. Now I'm going to check out what my y values are doing on the right side, which is also going up, so it's approaching positive infinity. We're just going to practice this with one more graph. Let's start with domain and range. Actually, let's start with filling out these two questions so that it can help us with this chart. So here it says, recall that a line the function will never cross is called, and this is called an asymptote. On the graph that I have provided, you will see those red dotted lines. Those red dotted lines are really not there because asymptotes are technically invisible, but I drew them in so you can see how it splits your graph. Okay, this vertical asymptote affects your domain because it cuts your graph from a left side to a right side, and you know that we read our domain from left to right. So as we read read this graph, we see that we would have to stop at this x value because of that vertical line. And that vertical line is the equation x is equal to -2. Then if I were to determine the range is going to be affected by this horizontal line because that is y is equal to 3. Remember, domains are in terms of x's and range is in terms of y's. So if you have these lines that are cutting your graph into two parts, we have to make sure that we exclude those values from the domain and the range. We have to exclude those values from the domain and the range. So when we're finding the domain, we see that this graph extends forever to the left. So it would start at -infinity. But as I continue to read my graph from left to right, I see that here at x is equal to -2, I would have to stop because the graph there does not go through that point. So we would stop at -2, and it does not include the value, so I would put a parenthesis. Then continuing on, we do have more on the other side of that line. And again, you see that it's getting infinitely close to that line, but it'll never touch. So we will start again with -2 to infinity. And again, you don't include those -2's because your graph never touches that line. For the range is affected by the horizontal line. So if you read your graph from bottom to top for the range, since we want to always start with the smallest value, this does go down forever, so we would say -infinity. But as I read my graph going up, I see that there is that horizontal, or rather this vertical break here, that causes, an excluded value from your range. So we would have to stop at 3. I'm going to not include it because no values go through there. And then I'm going to start again at 3 because it does go up forever. Now for your intercepts. And this intercept is kind of off. It's not really an exact number, so we can go ahead and estimate. Right here, this would be -3. That means that this line here would be -2.5. So I'm going to go ahead and say that this is -2.4, 0. And that would be my x-intercept. For my y-intercept, I see that it is located right here, right above the line of y is equal to 3, or right in the middle, rather, between y is equal to 3 and 4. So that means that my y-intercept is going to be 0, 3.5. Now remember that we determine increasing and decreasing behavior as we read the graph from left to right. So remember, the left is -infinity, the right is +infinity. And if I were to read my graph starting over here from the left, I see that my graph is only decreasing in this section. And then if I continue to the next, it is also only decreasing in this section. So my graph is never increasing because the whole time it is decreasing over the entire domain. So it is never increasing. And like I said, for decreasing, it is decreasing over the entire domain, we have to make sure that when we're writing increasing and decreasing intervals that it does match the domain that we are using. If I excluded a value in my domain, it most likely will be excluded in these as well, because that means that there's nothing on that point. So for decreasing, we would say it is decreasing from negative infinity to negative 2. Again, I can't, it's not doing anything at negative 2 because there's nothing there. And then it starts decreasing again from negative 2 to infinity. Remember what I said earlier for relative and absolute extrema. In order to verify that you do have extrema, your graph has to change direction, meaning changing from increasing to decreasing or decreasing to increasing. You're looking for those hills, you're looking for those dips. And as you can see on this graph, my graph is always decreasing, it never increases, so it's not changing behavior. And I can't see any hills or dips. So this particular graph has no extrema whatsoever, neither relative nor absolute. Now let's go on to end behavior. Let's start with the left side of the graph, so that will read as x is approaching negative infinity. Let's see what the y values are doing on the left side of the graph. And you can see here that it is neither increasing forever nor decreasing forever, but rather leveling out horizontally along some line. Now those horizontal asymptotes are going to affect your end behavior, because that's exactly what they do. They cut off your graph and does not allow it to either increase or decrease anymore. And it's leveling out and trying to approach where y is equal to 3. So this means as we read the graph all the way to the left, that's what as x is approaching negative infinity, f of x, my y values, are trying to go towards 3. Now remember, it doesn't touch 3 because that is an asymptote, but it is trying to get to 3. So that's where f of x is approaching. And on the right side of the graph, because that asymptote usually affects both sides, you can also see here that it is leveling out right above that line, but it's still trying to get to 3. Moving on to our next property, we're going to examine the symmetry of functions. Now there are 3 types of symmetry that we'll be checking out. There's x-axis symmetry, y-axis symmetry, and origin symmetry. Now, if you see a graph that has x-axis symmetry, that means that if you were to draw a line along the x-axis, it would cut your graph in half. You'd have that top half and the bottom half. And if you were to fold it over that line, they would land on top of each other. However, if I were to try the vertical line test here, I would see that this particular graph passes through 2 points, meaning that it is not a function. And we're only really concentrating on functions right now, so we won't see graphs that have x-axis symmetry. Therefore, you do not have to worry about this right now. Now, y-axis symmetry is another type of line symmetry, meaning that I would draw a line along the y-axis, and the left side would look the same as the right side. All functions that have y-axis symmetry are called even functions. Now, if we look at origin symmetry is not the same as line symmetry. This is rotational symmetry, and I have here the graph highlighted so you can see what happens if I were to rotate this graph 180 degrees, which it's not letting me do. So, let's try this. Here we go. If I rotate it 180 degrees, we do see that the graph ends up looking identical as to the original. So this is called origin symmetry. If you can rotate it upside down, it will look the same as the original. And these are all called odd functions. So even functions are symmetric along the y-axis, and odd functions are symmetric along the origin. Now, when you have a graph, it's easy to determine if it's symmetric. But we're going to look at how to test for even and odd functions given just the equation. So algebraically, what does this mean? Let's have a look at real quickly before we get into this at testing y-axis symmetry. rather for even functions. Let's say if I were to write out this coordinate here would be 1, 2. And this coordinate here is negative 1, 2. The x values are different signs, but I do notice that the y values stayed the same. So what do we do to test for even functions is we're going to plug in a negative x into the function. And if it looks exactly the same as the original, meaning the y values would be the same. So this would mean it is an even function and it is symmetric along the y-axis. Now you see here I put like what helps me remember E and E. E for even, E for exactly the same. So if you plug in negative x and you end up with a function that looks exactly the same as your original, it is an even function. So let's try that out. If I were to plug in negative x, then I would get negative x squared plus 4. When you apply the exponent here, this means you're doing negative x times negative x, and a negative times a negative gives you a positive, and this would be x squared plus 4. When I compare it to my original, you see that it is exactly the same. So this is indeed an even function. Now to test whether something is an odd function, we do the exact same thing. We plug in negative x, but if it is an odd function, it will not be exactly the same. It will be completely opposite to the original. So this is how I remember odd functions. If you plug in negative x, O for odd, O for opposite. Additionally, O for origin symmetry. They all go together, right? So all O's, basically. And just so you can understand, let's look at the graph of an odd function one more time. If I were to estimate these points right here, let's say this would be, I don't know, approximately x is 1.5, 2, and this would be negative 1.5, negative 2. We see that we have the x value and the negative x value, and you also see that the y values change signs as well. See, it's completely opposite, positive, negative, positive, negative. So that's why we do this. When we plug in a negative inside of an odd function, we should end up with a completely opposite function. So let's try that out. So if I plug in negative x, I get negative x raised to the third plus negative x. And if I work this out, keep in mind when you have a negative inside parentheses and you're raising it to an even exponent, so 2, 4, 6, etc., then it would become positive, because when you multiply a negative an even number of times, it's always positive. Versus if you plug in a negative and the exponent is odd, such as 1, 3, 5, 7, etc., when you multiply a negative an odd number of times, it will always be negative. So this negative x to the third would remain negative, and the x would be to the third, and then plus negative x would be minus x. And when I compare it to the original, you see that everything changed signs. What was x to the third is now negative x to the third, and what was a positive x is now a negative x. And since every single term is completely the opposite, this is an odd function, and it is symmetric along the origin. Now again, I also mentioned it down here in red. If you ever end up with some terms changing signs and some terms not changing signs, then we can't really determine anything about its symmetry. We would need more information that we don't have to worry about just yet. It would honestly just mean that it is neither an even nor an odd function, and I can't state anything about its symmetry, so you won't have to worry about it. But for the rest of these functions, when you're testing whether it's even or odd, you will also be required to let me know what kind of symmetry it has. So let's start with this first one. We have f of x is equal to x to the third minus 2x. So algebraically, when we're testing for even or odd, we're going to plug in negative x. And that would give me negative x cubed minus 2 times negative x. And when I simplify this, this will remain negative because it is an odd exponent, and then negative 2 times negative x becomes a positive 2x. And if I compare this with my original, we see that every single term changed signs. So this is an odd function. And if it's odd, that means it has origin symmetry. Over here, if I'm testing whether this one is even or odd, again, you're going to plug in negative x. And we would have 1 over negative x squared minus negative x to the fourth. When you apply these exponents, because this is an even exponent, this will become positive. And then we have this minus. And then when you apply this exponent, that negative x will become a positive x to the fourth. And again, when you compare to the original, we see that everything stayed exactly the same, exactly for even. This is an even function, and all even functions have y-axis symmetry. For this last one here, we have h of x, so I'm going to plug in negative x. And this would give me negative x raised to the fifth minus 2 times negative x to the third plus negative x. And if we clean this up, negative x to the fifth will become negative x to the fifth, meaning it remained negative. Then negative x to the third will also remain negative, but we're going to multiply with this negative 2, changing it to a positive 2x to the third, and then minus x. If you compare it to the original, we do see that every term changed signs. So since it's the opposite of the original function, this is odd. And because it's odd, it has origin symmetry, as we stated before. For this last one here, we're going to go ahead and plug in negative x again. And we get negative x raised to the fourth plus 4 times negative x minus 1. When we clean this up, negative x raised to the fourth becomes positive x to the fourth. Then this will be minus 4x minus 1. And if I compare it to the original, I see that x to the fourth remained the same sign, but the 4x changed signs. So since 1 didn't change, but 1 did, I already know that this function is neither even nor odd, and I cannot state anything about its symmetry. Now, a quick shortcut, that you can apply when you feel when you can, would be if you have polynomial type functions such as these, and you look at the exponents, if every single term has a variable such as an a, b, and c, every single one has an x value in it. And if, let's say, for example, in a, you see how all of the exponents are odd. When you don't see an exponent, that's a 1. And 1 and 3 are odd exponents. So chances are that's an odd function. Same thing with b, you see that the exponents are both even. And look how we got that it's an even function. And same thing with c. All exponents are odd, therefore this is an odd function. However, look at D. Yes, we have an even function and an odd function. So an even exponent and an odd exponent. So automatically I can say neither because the exponents are both even and odd. But if you have a constant at the end, a constant means a number without a variable, and then you have all even exponents, that means it is an even function. But if you had all odd exponents, then it would be neither because that constant would not change signs. But however, if that's too difficult to remember, whenever you have a constant, just go ahead and test by plugging in negative x. Now the last thing we're going to do is we're going to read a few scenarios and see how we can get information based on that scenario and its graph. Okay, so for this one, it says, with more people turning to the internet for news and entertainment, internet advertising is big business. The total revenue R in millions of dollars earned by U.S. companies from internet advertising from 1999 to 2008 can be approximated by, and then you have that equation, where T represents the number of years since 1998. So what I like to do before I even look at the questions, I like to label my axis so I know exactly what it is I'm looking at. Now, because T in our function notation is what is in the parentheses, that represents your x-axis. So this here is T for time, which in this case is years. Then in function notation, the whole thing, so R of T, that is your y-axis, which represents revenue, which we should know that revenue is in millions of dollars. So now I'm ready to see what these questions are exactly asking. This one says, use the graph to estimate total internet advertising revenue in 2007. However, when I look at my t-axis here, it's not in years. I mean, it is in years, but it's not represented by 1999 through 2008. We have these numbers instead. Now, it tells us that these values, the revenue, can be approximated using the equation and the graph from 1999 to 2008. And here we have this inequality where t is between 1 and 10. That means that 1 corresponds to 1998, and then 10 corresponds to 2008. So if I want to know the revenue for 2007, if 1999 is 1, then 2000 is 2, 2001 is 3, 2002 is 4. Then if you just continue counting up, by the time you get to 2007, you would get that t is 9. So if I want to estimate the total revenue, I'm going to go to t is equal to 9, and I go to that point. Then I go ahead and follow it to the y-axis so I could see what value it lands on. Notice that each line is 1,000, and we have 5 spaces in between. That means that each little block between 3,000 to 4,000 represents 200. So if I am going to estimate R of 9, that means my revenue, when t is equal to 9 years, I would say this is approximately 3,000, 3,200, and then 3,400. But remember, in the problem, it's told to us that revenue is in millions of dollars. So I'm going to have to add 6 zeros to that. So what does this mean? That means that in the year 2007, total internet advertising revenue is approximated to be $3,400,000,000. Now let's have a look at this following question. Use the graph to estimate the year. So now I want to know what the t value is going to be, in which total internet advertising revenue reached 2 billion. If these numbers represent in millions, 2 billion would be this one right here. 200,000 million is the same as 2 billion. So if I just follow this so I can get that t value, which is right here, that means that t is equal to 6. But the question is asking specifically for the year. So again, if you just count, 1999 is 1, 2000 is 2, 2001 is 3, 2002 is 4, 2003 is 5, so 2004 is 6. So in the year 2004, internet advertising revenue reached $2 billion. Let's look at one final example. An investor assessed the average daily value of a share of a certain stock over a 20-day period. The value of the stock can be approximated by the following function, where D represents the day of assessment. So D, that represents my x-axis. So D standing for days. And then the V of D, that's the value of the stock, which is my y-axis. in dollars. Now I'm ready to go ahead and use the graph to answer these statements. It says here, use the graph to estimate the value of the stock on the 10th day. So this is unlike the question before. We don't have to determine what each one of these values mean. Since this is in days, I'm going to go to t is equal to 10. And I see that this coordinate is 10.32. So $32 is the value of my stock after the 10th day. Then for this last one here, it says use the graph to estimate the days which the stock was valued at $30 per share. So that means I'm going to look at where the Y value is 30. And I actually have 3 answers because my graph does go through this a few times. Now over here we see that it's after 0 but before 1, so that means that in a few hours the value of the stock was already worth that $30. But since we're estimating the days, I would say that this occurs on the first day. Then again over here we just continue marking down those days. Again, on the 9th day the value of the stock was $30, and one more time here at 15. So after the 15th day, the value of the stock was also valued at $30. And that's it.